In this video, we're going to look at curved mirror drawings, and I'm going to show you how to do them. So the first thing you need to do is draw a principal axis, which is just a horizontal line. And we're going to start with a concave mirror. So you want to use a protractor to draw a curve, a circular curve where you're doing spherical mirrors. So it should be a circular curve. And then you're going to use your protractor to figure out where the center of curvature is, and you want to mark that with your pencil. So I'm going to mark the center of curvature for this one is 6 centimeters. So I'm marking that with a C. And then halfway between the center of curvature and the vertex, which is where the principal axis meets the mirror, is the focal point. And you need to mark the focal point too. So I'm going to mark center of curvature, and I'm going to mark the focal point. And make sure you measure those. And then we can move our ruler to the side for a minute. And we're going to start by making an enlarged image. So we're going to draw an object on our principal axis. And that object is going to be between this focal point and the center of curvature. So I'm going to use an arrow. You can use whatever object you want. It doesn't really matter. But I'm going to use a blue arrow. And so this is my object, and I can label it object with just an O. All right. And so then I'm going to remember my rules. So my rules are that rays parallel to the principal axis will reflect through the focal point, and rays that come from the focal point will reflect parallel to the principal axis. I'm going to use those two things to figure out where my image is. So you can take your pencil and make sure you use a ruler. That's very important. And you're going to draw a ray that goes parallel to the principal axis from the top of the object and hits the mirror, and then reflects through the focal point, like that. And then we want to take another ray that goes through the focal point, so from the top of the object through the focal point, and then reflects parallel to the principal axis. So those are your two rays. Now where they meet is going to be the top of your object. The bottom of your object, if you've drawn it originating from the principal axis, is going to be on the principal axis, because the rays coming from the bottom of the object are just going to bounce directly off like that. So, excuse me, you know that the bottom of the object is still on the principal axis. So now I can draw my image right here. And I can label it. With an I for image. Now here's my first drawing. I'm not done yet though. The fun is not over. What we need to do now is lost. Location, orientation, size, and type. So my first thing is my location. So I'm going to, over here. I'm going to measure the location of my image. And I can see that that's at like 6.8 maybe centimeters. So this is my DO, or DI, excuse me, equals 6.8 centimeters. My orientation is inverted. It's either going to be inverted or upright. My size is going to be the height. I'm going to measure the height of my image. Oops. It doesn't want to let me go off the page here. So that looks like maybe 2.3 centimeters. And that is HI. And remember that HI is negative when the object is upside down. So that was negative 2.3 centimeters. And then my type is real because my rays are actually converging here to make an image. So now I have done my drawing and I have located my image. You're still not done though. When you're doing this drawing, you're going to do the drawing and do the measurements, and then you're going to calculate what you should get for DI and HI. So remember that we have this equation, the thin lens equation also works for mirrors. 1 over distance of the object equals 1 over distance of the image. Sorry, 1 over distance of the object plus 1 over distance of the image equals 1 over the focal length. So you are going to use your focal length and your distance of your object to calculate your distance of your image. And then you're going to find a percent error of your measured distance of image. You're going to do the same thing with the magnification equation. You're going to use the magnification equation to calculate your image height. And for this equation, you want to use your calculated DI here to calculate your HI, and then you will find your percent error of your measured size from your diagram. And I have that all written out on the slide here, and I'll post all of this for you. So you're doing location, orientation, size, and type, and then you're doing percent error of DI and HI. Great, let me show you how to make the other two drawings. So now we're going to make a concave mirror drawing where we have a real image. And that image is smaller than the object. The first one, it was bigger. So my focal point, or my center of curvature, was at 6. My focal point is at 3. And I'm going to label those. So you will draw this on a new drawing. You will draw a new principal axis. You will draw a new center of curvature. I will warn you that when you're making your object, you don't want your object to be too big, because if it's too big, then the top of the object is going to be at a different distance from the mirror, a much different distance from the mirror than the bottom of the object. So you actually get a curved image, and so your percent error is going to be a little bit bigger. So make your objects a little bit on the smaller side. Okay, so we are going to, in order to make the image smaller, we're going to put the object outside of the center of curvature. So there's my object, and I will label it with an O. There we go. And then I'm going to follow my rules. A ray that goes parallel to the principal axis. And so you're using a ruler to draw a ray parallel to the principal axis, reflects through the focal point. You're using a ruler to draw these rays. And you're putting arrows on them so that you can see which way they go. And then a ray that goes through the focal point from the top of the object, goes through the focal point, reflects parallel to the principal axis. Now remember, rays are coming off of this object in all different ways. There are rays coming off of there going everywhere. But you are only focused on 2, and those 2, if you follow those rules, will help you find the image. And so now my image is right where the top of the image is, right where those, oops, let's draw the arrow first. Let's draw purple for image. And there's my image. You can see that it's smaller, and we'll label it with an I, just like that. And now we get to measure. So my location of my image is right at 5 centimeters. So that is DI equals 5 centimeters. My orientation is inverted. My size is maybe like 1.3 or 1.2. You can be much more precise than I am with this digital ruler. 1.3 centimeters out, and this is the HI. And also, this is negative because it's upside down, negative sign. And the type is real because those rays are actually coming together and forming a image. Goodness, I just messed that up somehow. Okay, so that is how you make your second concave mirror drawing, and then you would do the percent error of your DI and the percent error of your HI calculations. Now let's make a virtual image drawing. So this is where we have a virtual image, and we know that our virtual image is going to occur when our object is inside the focal point. So you're going to start with a new drawing. You're going to draw a new principal axis. You're going to mark your center of curvature and your focal length, and you're measuring these out. You're measuring your actual center of curvature and your actual focal point. Focal point is half of the center of curvature. And then we know that when we put our object between the focal point and the mirror, we're going to get a virtual image. So that's why when we are doing these observations, when you put that mirror, that concave mirror close to your face, that's where you saw the big image. When you had it farther away, that's where you saw the real images. So then we're going to follow our rules again. So a ray that goes parallel to the principal axis is going to reflect through the focal point. And then a ray that goes through the focal point. Now this is where it gets tricky. So here's what I do. I take my ruler and I line up my ruler between my focal point and the top of my object, because the ray is not actually going to come from the top of the object and go through the focal point and then to the mirror. It just has to come from the direction of the focal point. So your ray is going to come from the direction of the focal point, which would be like this. Hopefully you see how that extended would go to the focal point. And then it reflects parallel to the principal axis. Now notice that these two rays are diverging. Just like when you did your plane mirror drawings, the two reflected rays that you drew, they diverged. And when those two rays diverge, those reflected rays, you know you're going to have a virtual image because the rays aren't actually coming together. They're not forming a an image because they're a real image because they're not coming together. So you know you've got a virtual image. So here's what you're going to do. Same thing that you did with the plane mirror drawings. You're going to extend the reflected ray on the other side of the mirror with a dotted line showing that the light doesn't actually go there. And I probably shouldn't have the arrow on the end of there, but okay. And then we take this one and we extend the reflected ray on the back side of the mirror with a dotted line. And where those two dotted lines meet, that is where our our image is formed. And notice that this image is upright and it's larger, and it's always going to be larger for our virtual images on a concave mirror. Okay, so I need to label that with an I. I never labeled my O. Go ahead and label our O as well. And now I would fill out location, orientation, size, and type. I'm not going to do all the measuring because I think you've got the idea. But the location is going to be a negative number. Maybe I will do this. DI is equal to negative, and then we take our ruler, oops, and we measure how far it is behind the mirror. That looks like about 2.1 centimeters, and I made it negative because it's behind the mirror. Orientation is upright. The size is 2.6 centimeters, and that's positive, so that's HI. That's positive because it is upright. And then our type is virtual. Okay, there's that drawing, and then I would find my percent error of my DI and my HI using the thin lens equation. So the drawings that you need to turn in, there are 3 concave mirror drawings, 1 virtual image drawing, and then 2 real images, one where the object is between the focal point and the center of curvature, which will make a larger image, and one where the object is outside the center of curvature, which will make a smaller image. On those, you need to do location, orientation, size, and type, and then find the percent error of DI and HI. Now let me show you how to draw convex mirror, a virtual image. All convex mirrors make a virtual image, and there's only one type of image, so that's going to be a little bit easier than the concave mirror because there's only one type of image. So we're going to mark our center of curvature first. So you're going to draw a new drawing here, a new principal axis. We'll mark the center of curvature, and then halfway between the center of curvature and the mirror is the focal point. So this is going to look just like your concave mirror. The difference is that this is the back side of the mirror, right? And this is the shiny side of the mirror. So your focal point is behind the mirror. So remember in your calculations that your focal point is going to be negative. Now we're going to take our pencil and we're going to make an object. And the object can be anywhere. Oops, I wanted to make that blue. Okay, so there's my object. And now I'm going to follow the rules. I have a ray that goes parallel to the principal axis. It's going to reflect through the focal point. Now, how do I reflect through the focal point? That's a good question because the focal point's on the other side of the mirror, right? So this is another place where I'm going to use my ruler. I'm going to angle my ruler so that it lines up with the point where the ray is touching the mirror and the focal point. And I should do it like this. And then it's going to reflect along that line. So what happened to my arrow? There it is. So that's reflecting along that line, which if extended on the other side of the mirror would go through the focal point. So there's the first one. Then the second one is a ray that goes through the focal point is going to be reflected parallel to the principal axis. So once again, it can't go through the focal point because the focal point's on the other side of the mirror. So I'm going to take my ruler and I'm going to line it up with the top of my object and the focal point. Yeah, I'm having a hard time getting this to orient quite right on my computer here, but I think you get the point, hopefully. Okay, so then I'm going to line that up. So if the ray was going towards the focal point from the top of the object, it would reflect parallel to the principal axis. So I'm going to line that up. So if the ray was going towards the focal point from the top of the object, it would reflect parallel to the principal axis. So if the ray was going towards the focal point from the top of the object, it would reflect parallel to the principal axis. So if the ray was going towards the focal point from the top of the object, it would reflect parallel to the principal axis. So notice my two reflected rays here are diverging. And whenever you have your reflected rays diverging, you know that you're going to have a virtual image. So I'm going to take my reflected rays just like I did with my plane mirrors, and I'm going to extend them on the opposite side of the mirror with a dotted line to show that the light doesn't actually go there. This is just where my eyes think the light is coming from. And where those two extended rays meet, that is where your image is. Notice the image will always be between the focal point and the mirror, and it will always be smaller. So here's my image, and here's my object. You have to be able to do these drawings. This is something that is on, this will be tested. So make sure you know how to do them. If one isn't enough practice, then do more. They're so fun. Now I can fill out lost. So I measure my location of my image. It's about 2.1. And that image is on the opposite side of the mirror. So it's a negative image distance. My orientation is upright. My size is HI, which is equal to about 0.9 centimeters. And that's positive because it's upright, and my type is virtual. So what you need to turn into me is one drawing of a convex mirror. You need to do lost and then percent error of DI and HI. So you have 4 total curved mirror drawings to turn in. Quick little recap up here of these important things. This is the equation you're going to be using to calculate your expected DI, and then you'll use this equation to calculate your expected HI using your calculated DI here. Take note of the meanings of all of these things and when they're positive and when they're negative. We talked about that before. Also important notes, DI is negative if the image is behind the mirror, so it's a virtual image. HI is negative if the image is inverted. And don't forget, convex mirrors have negative focal length. All right, happy drawing.